Dr. Sridhar, back to you with another video session on efficiency calculation of single phase transformer. So this is our regular practice to determine the efficiency of any electrical machine, because already we did this for DC machines like DC generator, DC motor, and next three-phase induction motors also we have calculated, alternators, synchronous motor. For everything it is our regular practice, but this generally the efficiency of the transformer is very high because there are no rotating losses this transformer is going to have. So in today's video session, let us compute the efficiency expression for a single phase transformer, and in addition to that, what is the condition to get maximum efficiency. So these are the things we are going to discuss in today's video session. So coming to the definition, the ratio of useful output power to the input power. Of course, the output power is also useful only. Input power and output power we can easily compute because we were provided with different mathematical expression to compute input power and output power. Let us take the ratio between output power to the input power. Straight away we are going to get the efficiency. So this is the letter we are going to represent for efficiency. So efficiency is nothing but it is output power to the input power. So output power to output power plus losses. Now we can also take output power as a reference, or some of the cases you can take input power as a reference. Suppose the same expression we can put in some other form, like output power is nothing but input power minus losses to the input power. Like that also you can put up, or else output power to the output power plus losses is nothing but that is the efficiency. So again, more exactly what could be the losses means those are nothing but iron losses plus copper losses. So iron losses is nothing but it is represented with Pi, and copper losses are nothing but the P suffix C, or sometimes capital P suffix Cu may be used to indicate iron losses and the copper losses, Pa and Pcu. So here some standard nomenclature is required because in order to derive the expression for efficiency, now I am going to assume some of the parameters like V2 is nothing but it could be the secondary terminal voltage, and I2 is nothing but the full load secondary current, cos pi 2 is nothing but the power factor of the loads, and Pi is nothing but those are iron losses, which is nothing but hysteresis and eddy current losses, and Pc or sometimes Pcu is nothing but full load copper losses. These are nothing but I2 square into RES. Now what is this RES? Sometimes you can also represent it as R02 also. Why? Because now as we discussed in our previous videos that the internal resistance of the primary winding and secondary winding, better shift the total resistance, it should be available either in the primary or secondary, such that if we could transform the resistances as referred to the primary or as referred to the secondary, it will be very helpful for us. So that is nothing but whenever if everything is shifted to the secondary, now it was referred to the secondary. RES means equivalent resistance in the secondary, or sometimes this is also called as a R02. So because this is the resistance referred to the secondary. So consider X is the fraction of the full load. So how much of full load? So suppose if it is 100%, if you could take no problem, but 50%, 10% of the load, at that 10% of the load, what could be the efficiency? Sometimes people may ask. So that's why let me assume one X is nothing but that is the fraction of load. Fraction of load means which load? Fraction of full load. So 50% of the full load is nothing but X is nothing but the 50% or 0.5 of full load. Sometimes instead of X, people may represent with a small n. So n is nothing but that is a percentage of the or fraction of the full load. So the efficiency of the transformer regarding X is expressed as X times of output to X times of output plus Pi plus P square Cu. That is because why this X square into Pcu? This X is nothing but for this much of, or X is nothing but the fraction of full load. So fraction of full load means full load is nothing but corresponding to what? Secondary current. So if the load changes means proportionally current also changes. So load current, and whereas iron losses are nothing but the constant losses, and the copper losses are nothing but those are the variable losses. Once I changes or load current changes means proportionally currents also changes. So copper losses is nothing but this is I2 square into R02. Suppose if if this is nothing but X percentage of full load. If this is X percentage of full load means PCU at X percentage means this X into I2 whole square into R02. So this value is nothing but the X square into I2 square into R02. So what is this X square into? This is nothing but the PC at full load. That is the same expression we have represented here. So this is PI and this is X square into PC is nothing but the full load copper loss, and more or less anyhow this also we have represented here X square into I2 square into RES. But this will be, it means copper losses will be changed in proportion to the load, but whereas iron losses will remain changed, same. So the copper losses vary according to the fraction of the load. So this is the very, very important expression. This will be useful for calculation of efficiency at various loading conditions. So next, let me derive the expression for maximum efficiency condition. So when the efficiency of the transformer will become maximum and what it could be the condition to get the maximum efficiency out of the transformer. So we know that the efficiency of a transformer along with the load and the power factor, that is output power is equal to V2I2 into cos by 2, and denominator output power plus total losses instead of input power. So V2I2 cos by 2 plus PI plus I2 square into R02 or RES means as referred to the secondary. So this total expression, if you are dividing with I2 current, then V2 cos by 2 divided by V2 cos by 2 plus PI by I2 plus I2 into RES. Let us assume this is a equation 1. The value of the terminal voltage V2 is approximately constant because now we have discussed so many times and also we have ensured this value, that is the terminal voltage with respect to the loading condition, by calculating the voltage regulations also. Please refer our previous videos to get more information on this voltage regulation and what condition, why this terminal voltage is more or less constant for different loading conditions. So for a given power factor, the transformer efficiency depends on the loading current, because efficiency here, it depends, if you could keenly observe here, efficiency is nothing but it depends on the power factor and it also depends on the current. Anyhow, these iron losses are nothing but the constant losses. These losses are anyhow, these are nothing but the variable losses. So that's why, if you are assuming V2 is almost of all constant, then this efficiency depends on power factor and the loading current. So secondary current. And again, for at a common power factor, means for a fixed power factor, means indirectly we are also assuming power factor is also constant. Then efficiency is nothing but it depends on the load current. So in equation 1, the numerator is constant because V2 is already we have assumed more or less as a constant, and for a fixed power factor means cos by 2 is also constant. So 1 by R constant to constant plus variables. So this is the meaning of this expression. So and the transformer efficiency will be maximum if the denominator with respect to the variable I2 is equated to the 0. Only let us differentiate this denominator with respect to the variable parameter, that is nothing but the loading current. Let us equate that value to 0. So definitely we are going to get one expression. So that is nothing but D2 DI2 is equal to P2 cos by 2 plus PI by I2 plus I2 into RES. Let us equate this value to 0. Let us differentiate this. So we are going to get one expression, that is I2 square into RES is equal to P iron. This is a very, very important expression. So that is nothing but the transformer will give the maximum efficiency when their copper loss is equal to the iron loss. Means if the iron losses and copper losses are same, then that is a condition to see the maximum efficiency of the transformer. So efficiency maximum is equal to V2I2 cos by 2 divided by VI2 cos by 2 plus 2PI. Now here this is a 2PI only. Never it will be 2PCU. Why? Because PCU is nothing but it is a constant parameter. This is a variable parameter. So this PI is nothing but this is the correct way of writing iron losses is equal to copper losses. But instead of PI, of course, the condition is iron is equal to copper only, but never this must be PCU, because PCU is nothing but again it is a variable parameter. So that's why always 2PI we have to write to get the maximum efficiency, or else directly if numericals are available, just let us substitute the values, but it should not be equal to 2PCU. From equation 2, so what is this? This is the condition for maximum efficiency. The value of output current means at what current, at what load the efficiency will be maximum. Means load is nothing but this is the value. So I2 is equal to square root of PI2 RES, or this is square root of PI2 R02. This is nothing but the condition, or that is the load at which these copper losses are equal to iron losses, and also this is the point where the efficiency would be maximum. If X is the fraction of full load kVA at which the efficiency of the transformer is maximum, then this the value is nothing but already we calculated this. Copper losses will becomes X square into PCU, where PCU is the full load copper losses and this iron losses are nothing but this is the PI. So even if you are simplifying this expression also, you will get the condition for maximum efficiency. So for maximum efficiency, X square PCU is equal to PI. So again, at what percentage, that also you can calculate. X is equal to square root of PI to PCU. Let us say this is equation number 3. Thus output kVA corresponding to maximum efficiency is nothing but X already we have calculated. So efficiency maximum is equal to X into full load kVA. And putting this value of X from the above equation in equation 4, this is nothing but already we have calculated X value. Let us substitute there. So you will get the finally efficiency maximum. And after this again you can simplify this equation such that what exactly PI, what exactly PCU means. So efficiency maximum is equal to full load kVA into square root of iron losses divided by the copper losses at full loads. So this is the equation 5. It gives the maximum efficiency condition of the transformer at per percentage load also. So this is the formulas. It will be helpful for us to determine the condition for maximum efficiency, and also this tutorial session also helpful for us to determine at what percentage of the load the efficiency becomes maximum. I hope you all enjoyed this video. Thank you for watching this video. Thank you very much.
Like, share and subscribe. Hit the bell icon for more updates.